that the astronauts read out.
The gravitational effect of those planets.
Hi, I'm Lee and this is NASA Now. I'm sure you know that NASA is in the business of studying aircraft. Well, today we're going to visit one of NASA's busiest aircraft design facilities, the Icing Research Tunnel, where scientists and engineers are learning new ways to build safer and more reliable aircraft in cold and icy flight conditions. That's ahead. First, here's what's happening at NASA Now. Mapping the moon to determine its interior structure. That's the goal for NASA's GRAIL mission. The Gravity Recovery and Interior Laboratory launches in September. Its primary objective is to determine the structure of the lunar interior from crust to core. NASA scientists believe that by learning more about the structure of the moon, we can gain greater insight into the evolution of Earth and our neighboring planets in the solar system. Now let's take a look at the past.
Way back in 1944, the military turned to NASA to solve a problem. Its World War II pilots were losing control of their planes when flying over the Himalayas delivering supplies to our troops. That problem stimulated the development of the Icing Research Tunnel, still in active use today, saving lives.
We're at NASA Glenn Research Center in one of the world's oldest and largest refrigerated wind tunnels that studies aircraft icing, and we're joined by icing specialist Judith VanZante. What is the purpose of this icing tunnel?
Here in the Icing Research Tunnel, we simulate flight through an icing cloud. If you're on an aircraft, you want to make sure that certain surfaces stay ice-free. So typically we care about the wings, which generate lift, and we care about the propulsor, which pushes the airplane forward. So we'll take those components and test them here in the tunnel.
To simulate these flight conditions, you need to make it windy, cold, and wet. VanZante says it can be a very punishing environment. How cold does it get in here?
We can get down to minus 25 degrees Celsius. That's about minus 10 degrees Fahrenheit. Now water just starts to freeze at 32 degrees Fahrenheit, but that doesn't necessarily freeze solid. So as you go up in altitude, the air temperature gets colder. And the water droplet comes in and will phase change on the airframe, and that's where you get icing.
If the ice is not cleared away, it could negatively affect the performance and handling of the aircraft. What is the effect of ice if it stays on the airplane?
Ice forming on the leading edge of the wing would cause an increase in drag that the engines would have to work harder to overcome, and also a loss in the maximum lift. So the airplane would fly slower or require more fuel to fly the same speed.
So what are some of the ways that we've already discovered to remove ice?
On the ice protection systems that are designed for your aircraft come in several flavors. We call anti-icing systems. That's where you take heat and heat the leading edge of the wing so hot that the water droplet evaporates on contact. You typically see those on jets. On a turboprop where you can see the propeller spin, that's typically where you see the black rubber boot. That's a de-icing system. You have to let the ice form and then you inflate the boot and break off the ice.
In order to do a test, this gigantic 25-foot diameter fan starts the wind as it travels around a continuous rectangular loop.
So this is the fan area. Come with me, we'll take a look around the rest of the loop. Airflow is coming this way into the C corner. This is where we're standing. These turning vanes turn the air 90 degrees to come around into the face of the heat exchanger. There's coolant in these tubes that will chill the air down to this minus 25 degrees Celsius, and the fins will help radiate that heat and trap any liquid moisture that's still circulating around the tunnel. So we've made it windy, we've made it cold, now let's go to the spray bars and make it wet. This is where we create the cloud. We've got 10 spray bars with each nozzle there will shoot out a stream of water, and the cloud will come through here blasting into our model region. We'll have usually a wing section mounted in here, floor to ceiling, right in the middle of the turntable.
They have also been known to test engines, propellers, and helicopter blades. Last stop in the loop, the diffuser, which slows the airflow back down.
You guys stay here. I'm going to walk down and show you what we call the Alice in Wonderland effect. Ta-da! So we've gone from 6 feet tall in the test section down to 14.5 feet tall here. That completes the loop. Thanks for joining me.
Did you know that the 12 fan blades of the Icing Research Tunnel are actually made out of wood? Not just any wood, but wood from the Sitka spruce tree in British Columbia. Now you know.
Now it's time to check out what's up.
Next time you're on an airplane and seated next to the window, check out the speed brakes or spoilers located on the trailing edge of the wing. These parts of the wing are used to increase drag during landing.
Now that you know what goes into icing research, here's something you and your students can do. Check out this activity.
Ever wonder why a plane is able to fly and what function the different parts of the wing have on the performance of the aircraft? Our expert has assembled a pop quiz designed to give you and your students a better understanding of the physics of flight. Look for it on the NASA Explorer School's virtual campus.
Well, that's it for NASA Now. Be sure to tune in next time when we learn all about aerobraking. We'll see you then on NASA Now.
NASA Now comes to you from the virtual campus at NASA Explorer Schools.